Hello there, everybody, and thank you for joining me today for this review lesson about limits and continuity. You can see the main ideas for this review today. There's a lot of them. Let's get to it. So let's start today by talking about the concept of a limit again, and in order to do so, we have to discuss the concept of a one-sided limit. So on the screen there, we've got this graph, and we're going to evaluate some one-sided limits, and that will lead to the idea of a two-sided limit. So starting with the limit as x approaches 2 from the right. As x approaches 2 from the right, here's x equals 2. As x approaches 2 from the right, our function is approaching a y value of 5. So this limit would be equal to 5. Directly underneath that, we have the limit as x approaches 2 from the left. Well, as x approaches 2 from the left, this function approaches a y value of -1. Now, because those two values are different, the two-sided limit here does not exist. It does not exist because the limit as x approaches 2 from the left of this function is not equal to the limit as x approaches 2 from the right of this function. If the one-sided limits aren't equal, the two-sided limit does not exist. There's a jump here. Compare that to the limits around x equals 4. As x approaches 4 from the right, as x approaches 4 from the left, our function is approaching a value of 2. Of course, there's a hole there, but limits don't care about that as much. It's the behavior and where the function is headed. And so the two-sided limit here is equal to 2 because the one-sided limits were both equal to 2. Of course, f is not continuous at x equals 4. We'll talk more about that a little bit later. So when we have a graph of a function in front of us, we can evaluate limits using, that kind of logic. But how do we evaluate limits algebraically? What are our options if we don't have a graph in front of us? Well, here are the options, and this is kind of the hierarchy that I would follow to a certain extent. First, we can try direct substitution, where we take our limiting value, substitute it in, and try to get the value of that function. The downside there is that only works for functions that are continuous at that limiting value. We can also use properties of limits. A typical AP style question would be when you have a combination of f, g, and h, and you're finding a limit of that, knowing those limiting values. We can use properties to help us out there. When direct substitution fails and we get 0 over 0 or some other indeterminate form, we've got some other techniques that can help us, like factoring, rationalizing, L'Hopital's rule for those indeterminate forms. We'll practice that algebraic manipulation as well. Now, direct substitution is pretty straightforward, and so I'm not going to show that here. I want to look at some of that algebraic manipulation, starting with the limit as x approaches 3 of x minus 3 over x squared minus 9. If you were to try a direct substitution here, you'd get 0 over 0, resulting in that indeterminate form. We could do L'Hopital's rule here as well, but I want to save that a little bit later. Right now, I want to show you some of that more basic algebraic manipulation. And in this case, factoring is that algebraic manipulation, where we factor that difference of squares, which allows us to then cancel out these x minus 3's, and now we can make a direct substitution. We can plug 3 in for x, and we can get the value of this limit. Scooting over to this example, here you would also get 0 over 0, and it is possible to factor here as well. X minus 4 you can think of as a difference of squares, admittedly a little bit unorthodox, but you could factor it this way and then, cancel and go from there. But I also want to show you another technique that you may or may not like better, and it's, in one sense, kind of like rationalizing in a way, where we're going to take this limit as x approaches 4, and we are going to multiply the top and bottom by the conjugate of that expression with the radical in it, the conjugate being the square root of x plus 2. What happens here then is in the numerator, when you FOIL the numerator out, you'll get x minus 4, which will then cancel with the x minus 4 that's in the denominator here. And now all of a sudden we can make a direct substitution again. 1 over the square root of 4 plus 2, which will end up being 1/4. Factoring would have worked there as well. L'Hopital's rule should have worked there as well. Speaking of L'Hopital's rule, I want to practice that here. If you try direct substitution, subbing in 0, you'll get 0 over 0, which is one of those indeterminate forms. Let's give L'Hopital's rule this time chance now. We apply L'Hopital's rule by finding the limit of the derivative of the numerator over the derivative of the denominator. In the numerator up there, I needed the chain rule to differentiate e to the power of 2x. And now when I make a direct substitution, my denominator is 1. Here, this would be 2 times e to the power of 0. That'd be 2 times 1, which is 2, giving us a final answer of 2. So when direct substitution fails and we get 0 over 0 or some other indeterminate form, we can try factoring, multiplying by a conjugate, or L'Hopital's rule. Now, one connection between limits and the behavior of functions is this concept of limits at infinity and how that helps us to identify horizontal asymptotes. In fact, that's exactly how we identify horizontal asymptotes. We identify the value of the limit at infinity of the given function in question. Now, in order to evaluate limits at infinity, we can use the leading term test for rational functions. We could use L'Hopital's rule and logic for everything else. So here's a rational function g of x. Let's identify any horizontal asymptote that this rational function might have. Now we do so by evaluating the limit as x approaches infinity. But now for rational functions, we can use the leading term test. The idea here is that the highest degree terms will dictate the end behavior of this rational function. And so we really can just focus on those. And we can then reduce this fraction down to just 6 over 4, which, is a constant itself of 3/2. So this rational function has a horizontal asymptote, y equals 3/2. This function h here, the leading term test will not quite work. We've got this e to the power of x that's kind of messing things up. If we try to evaluate the limit as x approaches infinity, the numerator will grow without bound, and that's an infinity sign there, and the denominator will grow without bound. We get this indeterminate form here. So let's try L'Hopital's rule. Let's take the limit as x approaches infinity. Now I need the derivative of the numerator and the derivative of the denominator. Well, even here, if we think about this, the numerator and denominator will continue to grow without bound. So let's try L'Hopital's rule again. Here's round 2. The derivative of the numerator over the derivative of the denominator. Well, if we think about letting x go to infinity now, the numerator is what it is too, but the denominator will continue to grow without bound. And in that situation where the numerator is fixed, but the denominator continues to get bigger and bigger and bigger, this fraction is approaching a value of 0. That's where the logic comes into play. And so this function will have a horizontal asymptote at y equals 0. The next concept that follows after limits is typically continuity. That being because the definition of continuity relies on our understanding of limits. So let's start with that definition of continuity here. From a calculus perspective, a function is continuous at a value c if f of c is defined, the two-sided limit at c exists, and that limit is equal to f of c. All of this basically says there's no hole there, there's no jump, there's no vertical asymptote using kind of calculus notation. Now I'm going to add to this just kind of an extended version of this definition. We need the two-sided limit to exist. We need it to equal f of c. For the two-sided limit to exist, the one-sided limits have to be equal. And oftentimes we have to establish that, and so I want to add that to my notes here. We need the limit as x approaches c from the right to be equal to the limit as x approaches c from the left. That would establish that the two-sided limit exists, and then we need that to be equal to f of c. Let's practice applying that definition here. We've got f equaling this piecewise function, which is split up on either side of x equals 0. We need to show that this function is continuous at x equals 0. Well, what do we need to show? We got to show all of this. That the one-sided limits at 0 are equal, and that those values equal f of 0. So let's start with the limit as x approaches 0 from the left. Now, if we're approaching 0 from the left, we're talking about this top piece in our function here, and that function is given by 1 minus 2 sine x. Let's try a direct substitution here. Let's sub in 0. That's 1 minus 2 sine of 0, where sine of 0 is 0, and so this limit is equal to 1. Let's check the limit as x approaches 0 from the right. Now, approaching 0 from the right, we're looking at this piece of the function. That's e to the power of negative 4x. Well, if we make a direct substitution here, that's e to the power of 0, which is also 1. Now, this last part is somewhat trivial for a piecewise function that only has two pieces, because f of 0 will be using this top piece because that's where x is equal to 0. We already know that's going to be equal to 1, but let's go ahead and show it anyway. This becomes more interesting when there's more than two pieces to a piecewise function. So all of this information concludes for us that f of x is continuous at x equals 0. Because we've established that the two-sided limit exists, it's equal to 1, which is also what f of 0 is equal to. There's more ways that you could write that, but that's what I went with there. A typical type of AP-style question is like this one here, where you have a piecewise function. You need to find the value of some constant that will make the function continuous. Let's think about what needs to happen for that to be true. For f of x to be continuous at x equals 2, which is where the domain splits here, we need the one-sided limits at 2 to be equal. And then we also need those to be equal to whatever f of 2 is. And again, that'll end up being somewhat trivial because there's only two pieces here. Technically, that's what we need to have happen. From a more practical perspective, here's what I like to describe it as. For all of this to happen, we need the piece to the left of 2, that's x squared minus c, to be equal to the piece to the right of 2, that's 7x plus 2c. And we need these two pieces to come together at x equals 2. We need them to be equal at x equals 2. What that allows us to do is substitute 2 in for x, and then solve for c. So we sub 2 in for x, that gets us this far. Now we can solve for c using a couple of algebra steps, and we get the value here that would make this piecewise function continuous. Very typical type of AP question in regards to continuity. Now, one major idea that comes out of the continuity of a function is the Intermediate Value Theorem, abbreviated IVT. And the Intermediate Value Theorem says that if a function is continuous on a closed interval a to b, that function will take on every y value between the endpoints, f of a and f of b, at least once on that interval. In other words, if a function is continuous, that function cannot skip any y value between the endpoints. Can't do it. Can't pick up your pencil. Can't do a jump. Can't make a hole. Can't make an asymptote. Got to hit everything between f of a and f of b if that function is continuous. That's the detail we need to have there. We could be asked multiple choice questions about IVT. We could be asked free response questions as well. And here's one such example. The height of a tree is modeled by a continuous function h of t above. Selected values of h of t are shown in the table. For 2 less than t less than 10, must there be a time t when h of t is equal to 8, and we must justify our answer. I first want to highlight this phrase here. Must there be a time t? That phrase right there is a red flag for us that we are either applying the intermediate value theorem here or something we'll talk about in another review lesson, the mean value theorem. The mean value theorem deals with rates of change, and I don't see anything about prime or rates of change here, so I'm sticking to IVT on this example. Now, if we think about it, this question is asking us, between 2 years and 10 years, is there a time when the height of this tree is 8? Well, if you think about it, between years 5 and 7, the height jumps from 6 to 11, but the growth of this tree is continuous, so it's got to hit everything between 6 and 11, including 8. So yeah, there's going to be a time when the height of this tree is 8 meters. But how do we justify that, making sure that we've hit all the important points? Well, here's how I think about it. First of all, we've got to establish that we can actually apply the intermediate value theorem here. And remember, the intermediate value theorem applies to functions that are continuous on the interval in question. Well, we're flat out told that in this problem, but it's a good idea to make a note and write that down. The next step we have to take is to show that the endpoints of this interval are on either side of the number in question, showing that 8 is between the starting y value, the starting height, and the ending height. Well, let's start with the first part of our interval at t equals 2. H of 2 from the table is equal to 1.5. At the end of our interval, h of 10, the height of the tree at 10 years is 15 meters. Well, 8 does fall between 1.5 and 15, so we're looking pretty good here. But let's summarize this in a nice little concluding statement. Multiple ways you could write this. Here's what I'm going with. I'm going to say, since h of t is continuous, going to abbreviate that just to pick up the pace a little bit. And we also have to show that we know this is important. We found that h of 2 was on one side of 8 and h of 10 was on the other side of 8. Since all of that happens, we can say the IVT, and I'm going to abbreviate that, says, and now I'm basically going to copy and paste what the question says. There is a time t, excuse my handwriting, on the interval from 2 to 10, such that h of t equals 8. Such a free response question, probably worth 2 points. 1 point that you know that you need to rely on the intermediate value theorem here. Another point that you have included all the details. This detail here and this detail here. We just spent a good deal of time talking about continuity, the definition, some results of that definition, but we need to talk a little bit about discontinuity as well. In particular, the different types of discontinuity, removable and non-removable. It's important that we understand the difference between the two, and we can tell the difference algebraically. Of course, if we can graph the function in question, we can just look at the graph, see if there's a vertical asymptote there or a jump there or not. But for a no calculator question, we've got to know how to make the distinction algebraically. And the way that we can do that for a rational function like this is by doing a little bit of factoring here. In the numerator, factor out a 2x. We're left with x plus 5. In the denominator, we use our quadratic pattern here and factor accordingly. Points of discontinuity will make our denominator equal to 0. Well, I see two such points. I see x equals -5 and I see x equals -3. Those are 2 points of discontinuity on the graph of g of x. But we have to tell whether they're removable or non-removable. And the way that we tell is whether or not that factor will cancel out. Here the x plus 5's cancel, and that makes x equals -5 a removable discontinuity. If we graph this, it's going to show up as a hole on the graph. X plus 3 did not cancel out. That makes x equals 3 a non-removable, x equals -3, sorry, a non-removable point of discontinuity. That's going to show up as a full-fledged vertical asymptote. This one will show up just as a hole. To connect it back to limits here before we wrap things up, a removable discontinuity can also be identified using limits. This removable discontinuity can be identified by the fact that if we were to do the one-sided limits at x equals -5, they would be equal to each other. But what makes this a point of discontinuity is that this function is not defined at exactly x equals negative 5. But the one-sided limits are equal, which gives the appearance of an infinitely small hole at x equals negative 5. That was a lot of information in a little bit of time. Tried to hit some highlights in regards to limits and continuity. Thank you for watching.